Assignment 6 is due on Wednesday, 4/21. Second exam is going to be on Monday, the 12th. And the final exam will cover chapters 6 and 7, and that's on Wednesday, the 28th, I believe. Let's see. So final exam Wednesday, April 28th, 12:30 to 2:30. 12:30 to 30. We'll meet, here in Collaborate Ultra as usual. And assignment 6, that's online. So 4 problems on induction. And, we should finish our presentation on induction pretty soon. So induction is, something that's got, a definite template to it, a type of proof that's got a template, like, built in. So, like, we're going over the template several times so that you know what that template is. And then, each problem is, in and of itself something different. Could you show how to get started proof? Yeah, so on the current homework, you have to break down the partial order on pairs into terms of the partial orders on each element. On each coordinate. So you're asking about number 4, right? Yeah. So on assignment 5, problem 4, right, what is it? x1 comma y1 is less than or equal to x2 comma y2 when either less than or equal to with an A is partial order on A, and less than or equal to sub B is partial order on B. Define x1, y1 less than or equal to x2, y2 in A cross B when either 1, x1 is less than in A, x2, so that's meaning x1 is less x1 is less than or equal to in A, x2, and x1 is not equal to x2. Or 2, x1 equals x2, and y1 is less than or equal to in B, y2. All right, so to show this is a partial order. On A cross B. So there's 3 symbols in use here. Okay, this is defined on pairs in A cross B, and you're trying to show that this symbol is a partial order on A cross B. This symbol is a partial order on A. And this symbol is a partial order on B. This symbol applies neither to A nor to B. It only applies to A cross B. This symbol applies to A, but does not apply to B, nor does it apply to A cross B. So when comparing elements of A, you must use this symbol. When comparing elements of B, you must use this symbol. And when comparing elements of A cross B, you have to use this symbol. All right, so show that this is a partial order on A cross B. So you got to show it's reflexive. That one's easy. Symmetric. So let me start the reflection.
Anti-symmetric.
Or anti-symmetric, right? Anti-symmetric. Let me start this one. So let x1, y1 be an element of A cross B. Then x1, y1 is less than or equal to x1, y1 because done. Okay, so that should be the way it looks. There's something very similar to that. x1, y1 is less than or equal to x1, y1 because, well, you know, it has to somehow satisfy either one, which it certainly can't, you know, or 2. So it must be that it satisfies 2. So you say y. All right, and remember that you already know that less than or equal to sub b is a partial order on B. Antisymmetric. Okay, suppose that x1, y1 is less than or equal to x2, y2, and x2, y2 is less than or equal to x1, y1. So now you want to show that x1, y1 is equal to x2, y2. All right, well, this means what? So by definition, x1, y1 less than or equal to x2, y2 means what?
Does it mean they're equal?
Nope. The definition is right up above.
X1 is what is it, less than sub A than X at sub 2, or X1 is equal to X2, and then Y1 is less than or equal to sub B, Y sub 2.
All right, so now you need to consider each case separately. Right? Well, let's just do it that way. So,
That's what I've been struggling with.
right, now you have to set each case separately. So if x1 is less than in A to x2, then because, well, then again by definition, x2 is less than in A, well, x1, or x2 equals x1 and y2 is less than or equal to in B, y1. So, well, if, oops, shouldn't be there. Okay. Well, if x1 is less than in A, x2, it can't be the case that x2 is less than in A, x1 by antisymmetry. Cannot be the case. So that's not possible. Nor can it be the case that x1 is equal to x2 when x1 is less than in A, x2. So both of which are impossible. So write an appropriate sentence here, such as both of which are impossible, period. Okay. Second possibility, if x1 is equal to x2 and y1 is less than or equal to in B, y2, then, again by definition, all right, well, if x1 is equal to x2, this one is impossible. Therefore, it's got to be this possibility. And therefore, y2 is less than in B, y1, less than or equal to in B, y1. So you have that x1 is equal to x2, and y1 is less than or equal to y2, and y2 is less than or equal to y1, which implies what?
y2 equals y1.
Why? Yes, why? Why is that? Because this is what? What is that?
A partial order on B.
It's a partial order. We assumed it's a partial order, so it satisfies the properties of being a partial order. Antisymmetry being one of them. Period. Right, so there's four possibilities, right? I mean, this has two possible meanings, and this has two possible meanings. So there's actually four possible meanings, but, meaning A here, and meaning A here, meaning A here, meaning B here, meaning B here, meaning A here, meaning B in both. But actually only one of those four possibilities is actually possible. The others are not, for various reasons. All right, so in general, when you conclude that either P or Q is true, then your proof splits into two cases. Usually, not always. Okay, usually it means your proof splits into two cases. All right, so by definition, this is true or this is true. In the first case, if that's true, then blah 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 blah. Period. If the second possibility is true, then blah, 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 period. So your proof splits into two subproofs whenever you have either this is true or that is true. Okay? So that's antisymmetric, and then transitive. Right. Suppose that x1, y1 is less than or equal to x2, y2, and x2, y2 is less than or equal to x3, y3. Now show that x1, y1 is less than or equal to x3, y3. Right? So again, there's two possible meanings for that and two possible meanings for that, which gives you four possibilities in general. So you split into two cases again. Right? So as in the previous case, don't say that. So by definition, if x1 is less than x2 or x1 equals x2 and x2 is y2 is less than or equal to in B, or no, y1 is less than or equal to in B, y2. Why? Why is this true? Where did I get that from? by definition. Where's the definition? Where's the definition of x1 less than or equal, x1 y1 less than or equal to x2 y2? Well, it's given in the problem. The definition of what it is right here. Essentially, given a partial order on a set A and partial order on a set B, you can get a partial order on the Cartesian product A cross B in a couple of different ways. Okay, this partial order is called the lexicographical one. And then there's that other one where, we did it in class as an example. I don't know what you would call that other one. Anyway, this is the lexicographical one. Is actually the more common of the two. It's lexicographical because it's like alphabetical ordering. All right, so once you're here, then if x1 is less than in A, x2, then blah, 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 period. If x1 equals x2 and y1 is less than or equal to in B, y2, then blah, 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 period. Okay? So, same as before. What else on this assignment? Any other questions?
Could you help with the transitivity part for number 3?
Transitivity. Okay, number on the divisibility partial ordering. So number 3. All right, so the transitivity part. So suppose A divides B and B divides C. So by definition, there is K and L in this set of integers, or natural numbers, such that AK equals B and BL equals C. And now do some substitutions. Okay, take the B equal to AK and plug it in here. And then, pretty much follows from definition right after that. What else?
This is more for the exam, but for the exam, are you allowing us to use the 1-page note sheet again?
Of course, sure. Yeah, one page of notes, 8.5 by 11, front and back. All right. So by 5 p.m., guys, and I'll have solutions posted after that. For the last two assignments, guys, please, get started on it earlier and send me, if you got questions, you want me to check over what you did so far, help you out a little bit. Send me a PDF of what you did. PDF, please, one PDF file of what you did, and I'll take a look at it for you. I got no problem doing that back and forth with you because that, is a learning experience for you. Having that back and forth. It's not the kind of thing where I teach you how to do integration by parts, and then I give you, a dozen problems to do using integration by parts. You do them all. I'm like, okay, that's right, that's wrong, that's wrong, that's right, that's partially right. It's not like that. We've got these classical problems like number 4. And we want to get it right. We don't want to get it half right. We want to get it right. So we need a back and forth. We need a discussion of some sort. Because it's an important problem. It's a classical problem. It's part of understanding what partially ordered sets are all about. It's not like just some random problem on integration by parts. Yeah? Or same with number 3. We want to understand, why is that a partial order? Or the partial order I presented on partitions. Like you have a set A, and you're looking at the set of all partitions of A. And that's the partial order under that refinement partial ordering we were talking about. It's a classical thing, we want to understand why it's so. We don't want to just do the problem, get half credit, and move on. All right? So get started a little earlier on assignment 6 and send me your work and we'll take a look at it, all right? All right, so back to induction. So again, the first principle of mathematical induction right here. To show that for every n, so P of n is a predicate. For every n, P of n is true over domain D, not the whole universe, just D being some consecutive domain of integers with the smallest starting point. Okay, so it doesn't even have to be infinite. It can be finite too. We can have a smallest member and a largest member. That's perfectly valid as well. So to show that for all n, P of n is true, you show that P1 is true. And for every n, Pn implies Pn plus 1 is true. This is called the base case. This is called the inductive step. So we did some examples. Here's the last one we had. Show that n factorial is greater than 2.5 to the n minus 1 for all n bigger than or equal to 4. So here the domain that we're using is 4, 5, 6, 7, 8, 9, ... We're not starting at a lower number than that. So starting at n equal to 4. Notice that P1, P2, and P3 are actually false. 1 factorial is 1, and that's not bigger than 1. 2 factorial is 2, and it's not bigger than 5 halves, which is 2.5. 3 factorial is 6, which is not bigger than 5 halves squared, which is 25 over 4, which is 6 1/4, still false. It doesn't become true until n equal to 4, in which case it stays true after that. So when n is equal to 4, so in this problem, Pn is this statement here. Oops. Is just this inequality here, right? That inequality is either true or false. It's false for n equal to 1, 2, 3, and we want to show it's true for n equal to 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 1 million, 1 million and 1, 10 zillion, whatever. It just remains true after that. So we start with n equal to 4. All right, well, when n equal to 4, n factorial is 24. And 5 halves to the n minus 1 is 5 halves to the third, which is 15.625. And you see that 24 is bigger than 15.625. All right, inductive step. Pn implies Pn plus 1. So we assume Pn is true for some arbitrarily chosen member of the domain, n equal to 4. Okay, so we assume Pn is true, and that assumption is called your inductive hypothesis, right? The first part of an implication statement is called the hypothesis. So this is our induction hypothesis. It's true for some n bigger than or equal to 4. Now, show that Pn plus 1 is true. What's Pn plus 1? Well, you take Pn and you replace n with n plus 1. So show that n plus 1 factorial is greater than 5/2 to the n. Show that that's true as well. All right, when proving an inequality, you must use a chain. Stacking inequalities simply does not make sense. Okay, it must be done in a chain. With equalities, you don't always have to work in a chain of equalities, although that's usually the way it's done. It's much more elegant and less, more clear. But with inequalities, stacking inequalities is just a no-no. It just does not work. Okay? It must be done in a chain. Now, the reason for each inequality in a chain might be, might require some subchain of, might require another chain of reasoning, and that's fine. So like this inequality requires some chain of reasoning, and this inequality requires some chain of reasoning, which itself is an inequality, which actually it is. It must be done this way, and all the inequality symbols need to point in the same direction. And as long as you have one strict inequality, you get strict inequality at the end. The first thing is strictly greater than the last thing. If you only have less than or equal to at every step, then you only get that the first thing is less than or equal to the last thing, because equality was a possibility all the way across. But here we have strict inequality actually in two places. All right, well, n plus 1 factorial, starting with the left, or you can start with the right, whatever works for you. N plus 1 factorial is equal to n plus 1 times n factorial, as we discussed last time. By the induction hypothesis, right, the induction hypothesis is that n factorial is strictly greater than 5/2 to the n minus 1, right? Therefore, a times n factorial is strictly greater than a times 5/2 to the n minus 1, as long as a is a positive number, which n plus 1 is, right? So your a times n minus 1, n factorial, is greater than a times 5/2 to the n minus 1, because n factorial is greater than 5/2 to the n minus 1. That's the induction hypothesis. So you have to state your induction hypothesis explicitly and state your target conclusion explicitly, and then you must say where that induction hypothesis is used. That's the gist of an induction proof. All right, so this is strictly greater than 5 plus n plus 1 times 5/2 to the n minus 1. Well, remember n was bigger than or equal to 4. N was bigger than or equal to 4. Therefore, n plus 1 is at least 5. So n plus 1 apples is bigger than 5 apples, right? And 5 is bigger than 5/2. So 5 apples is bigger than 2.5 apples, right? And then, 2.5 apples times, and then 5/2 times 5/2 to the n minus 1, you just, same base, and you multiply them together, so you just add the exponents. You get 5/2 to the n, and that's what we wanted, that n plus 1 factorial is strictly greater than 5/2 to the n. Let's do another one like that, inequalities. So in the homework, we've got one problem using inequalities. Right here, number 2. Doesn't use factorials or anything like that. It's just polynomial. Now, of course, you do not need induction to prove this. I mean, how does one prove that? You graph n squared for all real numbers. I mean, we're only using natural numbers. But you can graph it for all real numbers. It's that standard parabola. And then you look at the line 2n plus 3, right? And that line 2n plus 3, it's going to intersect the parabola in 2 spots, right? And then so the parabola is greater than the line before and after the first and second intersections. And then it's less than the parabola, like in between those intersection points, right? I mean, it's this kind of picture here. Right, so after this point, the parabola is greater than the line. You know, I mean, that's fine. That is a proof, and it's a much more elegant proof than what we're doing here. But this is just practice for induction. So use the first principle of induction to show that. Okay, just for practicing about induction. But let's do one more inequality problem. Show that. Prove that. So, what is it? N to the n is strictly greater than n factorial for all n greater than or equal to 2. N to the n is greater than n factorial. I mean, obviously it's the case. N to the n is this, right? N times n times n times n is definitely greater than n times n minus 1 times n minus 2 times 3 times 2 times 1. I mean, it's a painfully obvious statement, actually. Right? It's obviously true, because n is greater than all these numbers here except for the n. So the product is going to be greater. You know, products get bigger as the arguments of the product get larger. Okay, but again, we want to practice the induction. See how that works. All right. So base case. Right, in the base case here, n is equal to 2. Well, what's n to the n when n is equal to 2? So if n is equal to 2, then n to the n is equal to 2 to the 2 is 4, and n factorial is 2 factorial is 2, right? And 4 is bigger than 2. Period. Right, so so n to the n is bigger than n factorial for n equal to 2. Induction step. Right, again, Pn implies Pn plus 1. So assume that Pn is true. This is Pn. So assume n to the n is greater than n factorial for some n bigger than or equal to 2. Show that. Well, what's Pn plus 1? What's Pn plus 1? Sorry, go ahead.
N plus 1 to the n plus 1 is greater than n plus 1 factorial.
Yeah. All right. So actually, I'm gonna flip it around. I'm gonna start with the n plus 1 factorial. All right. N plus 1 factorial is equal to n plus 1 times n factorial, as we discussed. Right, and by the induction hypothesis, we get what? Excuse me. What do we get? All right, the induction hypothesis is that n factorial is less than n to the n. So this expression is less than what?
n plus 1 times n to the n.
Yeah. Excuse me. Right? Which is less than, and this is just because n is less than n plus 1, n plus 1 times n plus 1 to the n. Right? I mean, 3 to the n is less than 4 to the n because 3 is less than 4. Right? So, I mean, if I take the base of this exponential expression and I increase the base, well, then the result, and leave the exponent unchanged, then the result increases. And then this, just by basic algebra, is, your same base, you just add the exponents now. So n plus 1 to the n plus 1. And that's it. All right, so the first thing is strictly greater than the last thing.
Induction's kind of nice.
Yeah, it's very nice. It's a lot. I mean, it's an important tool in lots of areas. In some areas, it isn't. In many areas, it's not. All right. So far we've done a bunch of numerical examples, and those are great. Right? They're all fine, numerical examples. But it really gets sort of more exciting when you get into geometry. So in induction, it applies to not just geometry, but all sorts of combinatorial objects. Discrete objects or whatnot. I mean, that's just a really vague term. It's not a well-defined term, but the sort of basic discrete geometry things are things like you're familiar with from grade school. So here's one of my favorite examples. It's an example that's very close to my heart. So a collection of n lines, call it script L, is said to be in general position when 1. Every pair of lines in L intersect. So no parallel lines. All right, so a collection of lines, call it L, in the plane is just in general position when every pair of lines in L intersect. So 2 lines in L, they or 3 lines in L, they look like that. Well, 2 lines, they have some intersection points, so no parallel lines. And 2, no 3 lines in L intersect at the same point. So if you have 3 lines from your collection, they don't intersect at the same spot. They have to intersect in 3 separate spots. Line 1 and line 2 intersect somewhere. Line 2 and line 3 intersect somewhere else. And line 3 and line 1, they intersect at a third point. Right? So this kind of thing doesn't happen. You don't get that. So that's called general position. It's a very sort of pretentious term. I don't like it. It's pretentious because it's vague. It's just a very vague. The word general doesn't really mean anything in this context. The English meaning of general doesn't mean anything really in this context. So when you say it's in general position and you say, what's that? Speaking from personal experience, and when you're a young grad student, you say, what's that? And everyone's like, well, it means this, obviously. I was just kind of thinking it's not very obvious. So if you ever use a term that's kind of vague to mean something very specific, you should at least apologize. At least apologize to your audience. So I, on behalf of, the entire discrete geometry research community, apologize to you for this weird term, but I couldn't think of anything better. So there it is. Okay, so now when you have a collection of lines in the plane, it divides the plane into so many regions. So let's prove that a collection L of n lines in general position divides the plane into n squared plus n plus 2 over 2 regions. So it doesn't matter what they really look like, it's always that many regions. Oops. What do
you mean by region though?
Like how many regions we got here? 1, 2, 3, 4, 5, 6, 7, right?
Oh, I see.
Yeah. So it just, cuts the plane into so many regions. Like 2 lines, cuts the plane into 4 regions, right? So if the lines were perpendicular, like the x and y axis, right? X and y axis are perpendicular, then you get 4 regions. And, they have been immortalized as quadrants 1, 2, 3, and 4, right? But I mean, that idea goes really far, actually. So where's the predicate Pn that we're trying to prove? Where is the statement that is either true or false? The statement.
The regions are equal to was n squared plus n plus 2 all divided by 2.
Yeah, it's this sentence right here. Exactly it. This is Pn. It's a sentence that is either true or false. Right here. And so this is the predicate Pn. N lines. So it's always general position. So let's just sort of skip that for the moment. N lines creates n squared plus n plus 2 over 2 regions. It's not true when it's not in general position. I mean, here we've got 7 regions, right? If you had 3 lines not in general position, it's only 6. Right? That's only 6. But they're not in general position because they all intersect in the same point. All right, so that's Pn. N lines defines n squared plus n plus 2 over 2 regions. That's what we're trying to prove. So let's take an example. Right, so we did 3 lines already, right? 2 lines give you 4 regions, right? 2 lines make 4 regions. Right, and 2 squared plus 2 over 2, right? That's 8 halves, which is 4. Yeah. So now, whenever you have 2 lines, actually it always looks like this. I mean, up to whatever that angle is supposed to be. In 3 lines in general position, again, always looks the same up to changing the angle. I mean, here is an almost equilateral triangle. I mean, I could do this and it skews that triangle in the middle more. But it all really kind of looks the same, just by sort of tweaking the lines a little bit. Things are never really different with 3 lines, nor 4 lines, nor 5 lines. It's not until you get to 6 lines that stuff actually, 5 lines, that stuff actually changes. Like 4 lines always looks like this. And then 5 lines can look different. So like here, that's 5 lines. But this is also 5 lines. And this one is actually different than the one from before. And so that's 5 lines. But this is also 5 lines, and it's not, there's no star there. I mean, you don't see any star, do you? Right. There's no region that's a star. In fact, there's a region, you see this region here, it's a quadrilateral, 1, 2, 3, 4. That's a quadrilateral, but if I put that up here, no quadrilaterals. It's triangle, 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 pentagon. And then these regions are all unbounded. So that's 5 lines, and that's 5, copy it. So that's also 5 lines right here. If I take this line and put it down here. But 5 lines, despite the difference geometrically between this and this, 5 lines always makes 5 squared plus 5 plus 2 over 2. So it's 32 over 2, 16 regions. Now let's count them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. How about here? 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, 15, 16. Always the same number of regions, despite the topological difference between the arrangements of lines, as long as stuff is in general position. Okay, so let's do the proof by induction. So base case. Well, what should the base case be? I mean, to have an arrangement of lines, you need what?
2 lines.
Just a line, really. Yeah, I mean, lines or a line. I mean, just one line is fine. You could start with 2. We can start with 0. Actually, it works for 0 as well. So the base case, we'll just start with 1. So, well, 1 line. Boom. Defines how many regions. Clearly, right? And n squared plus n plus 2 over 2 is 1 plus 1 plus 2 over 2, which is 4 halves, which is 2. Right? As required. And geometrically, 1 line will make 2 regions of the plane. I mean, of course, these lines, they stretch infinitely in each direction, but so you have to imagine that. So 1 line defines 2 regions in the plane, and, n squared plus n plus 2 over 2 for n equal to 1 is 2. So they're the same. Induction step. So what is the induction hypothesis? You must assume Pn and then show Pn plus 1. So what do we assume?
Assume n lines divides a plane into n squared plus n plus 2 over 2 regions.
Yes, this is statement boxed up in red. So assume that any collection of n lines in general position divides the plane into that many regions. And so there is the induction hypothesis. Now we want to show that what? Right, that statement there is Pn. And we want to show Pn plus 1. Oops, there should be a 2 there. Well, how do you get Pn plus 1? You take Pn and you replace n with n plus 1. So what is it? Replace n with n plus 1. So any collection of
n plus 1 lines
divides the plane into what?
n plus 1 squared plus n plus 1 plus 2
Yeah, region.
over 2.
That's it. Okay, so let L be some collection of n plus 1 lines in general position. Okay, we wish to show that L defines this many regions, but I want to simplify that expression. N plus 1 squared plus n plus 1 plus 2 over 2. So that's n squared plus 2n plus 1 plus n plus 1 plus 3 over 2 is equal to n squared plus 3n plus 4 over 2 regions. Alright, so we want it to be that many regions, but let's just simplify that expression. Write it like that, n squared plus 3n plus 4 regions. Okay, so let H be some line in L. Therefore, what? L minus just H by itself is what? Right, so L's got n plus 1 lines in general position. Take away 1. What's left over?
N lines.
There's a collection of n lines, which, what, are they still in general position, or did somehow things get messed up?
No, they're still in general position.
Still in general position, right? What's general position? Every pair of lines intersect. So if I take away a line, I still have every pair intersects. And no 3 lines intersect at the same point. So if I take a line away, still satisfies that property. So these types of properties are what's said to be inherited by subsets. So L is a set with 2 properties, and those 2 properties are both inheritable, meaning every subset of L inherits the same 2 properties. I mean, of course, not all properties are like that. In particular, existence properties, right? I mean, if L is a set for which there exists a special element called Daniel, right? If I take a subset of L, it may no longer have that property that it contains Daniel. Daniel may be someone that was taken away. right? So existence properties are not inheritable. Typically, universally defined properties are inheritable. That's a different topic. All right, so L minus H is a collection of n lines that are still in general position. So what? What did we assume about n lines in general position? What did we assume about n lines in general position?
That they were split into n squared plus n plus 2 over 2 regions.
Right, and that fact is called what? The
Inductive
induction
hypothesis.
hypothesis. So by the induction hypothesis, L minus H divides the plane into n squared plus n plus 2 over 2 regions. Okay, so now let's take H and put it back in. Now, line H intersects the n lines of L minus H at one point each because of general position. So line H, it intersects the other n lines at one point each. So line H has got n intersection points. So here's line H, and here's one of the other lines. So that's intersection 1. Here's another one of those other lines. That's intersection 2. Another one of those lines, that's intersection 3. So intersection point 1, intersection point 2, intersection point 3, blah, 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 intersection point N. You can do one more. Intersection point N minus 1, and then intersection point N. And this is line H right here. No, it's not. Yeah, that's intersection. That's H right there. Okay. So what's H doing? How many regions? So of the n squared plus n over 2, n squared plus n plus 2 over 2 regions, defined by H, or defined by L minus H, the line H passes through how many of them? Think about it before you say it. How many does H pass through? So there's this many regions defined by L minus H. And then I'm going to take H and put it back in. How many of these regions does H pass through? Well, it passes through every time it crosses a line. So how many regions did it pass through?
And it passed through an amount of lines.
Regions. How many regions did it pass through?
Oh,
Right, so like
well,
here's
you said that the amount of regions is equal to the amount of lines it passed through, right?
So, there's this many regions, n squared plus n plus 2 over 2 regions defined by L minus H. And now I'm going to put H back into the arrangement. And H is going to cut through how many of those regions. So here's a region. Here's a region.
it would be
Region.
was n squared plus n plus 2 over 2.
Nope. Here's another.
N plus 1?
N plus 1, yeah. Alright, so it passes through
That's
n,
kind of nice.
yeah, n plus 1 regions. So of the n squared plus n plus 2 over 2 regions, H passes through n plus 1 of them. And what does it do to each one of those regions when it passes through it? It takes each one of those regions and what? Does what to it?
It divides each region into 2 regions.
Each region traversed by H then divides it into 2 subregions. So, for a total gain of how many regions? So a total numerical gain of this much to the total number of regions. So each single region gets cut into 2 regions. So the big region is replaced by 2 smaller regions, thus increasing the number of regions by not 2, but just right. So I have a region, and I cut it into 2 smaller regions. So the gain in the number of regions is 1, not 2, right? All right. So like here's a region. There's a region. Right, there's a region, and now I take H and I pass it through there. So that region got cut into 2 smaller regions, 1 and 2. So the total gain in the number of regions is 1, not 2, right? Because taking away the big region. Take away the big region, replace it with 2 smaller regions. So I gain 1 to the number of regions. So H passes through n plus 1 regions, gaining 1 region each time. So the total number of regions is increased by how much? And we pass through this many regions, cutting each one into 2.
N plus 2.
No, just n plus 1 regions.
N plus.
Yeah. Each region gets replaced by 2 subregions. So the big region gets taken away and replaced by 2 smaller ones, therefore increasing the number of regions by 1 each time. So 1, n plus 1 times, gives you n plus 1. So L defines the following number of regions in the plane. Defines how many regions? So we're adding n plus 1 to what? All right, how many regions did L minus H give? It gave that many regions. And then we put H back in, and we increase the number of regions by that much. So L defines how many regions?
N squared plus N plus 2 over 2 plus N plus 1.
Regions in the plane. So that many regions in the plane. And where's my cursor? Come on. So that many regions in the plane, and is equal to n squared plus n plus 2 plus 2n plus 2 over 2, which is n squared plus 3n plus 4 over 2 as required.
Required.
Yeah, that's what we wanted. That many regions. N squared plus 3n plus 4 over 2. Right?
It's like 130, I think.
Oh my, guys, please, it's you really should stop me. Okay, I apologize. Have a good day, guys.